Okay, when you're making observations of phenomena in the process of research, you'll end up with data that exists on a certain kind of scale. And this is where the idea of scale theory comes from. So Stanley Stevens, in the mid part of the 20th century, published an influential paper on his theory of observation scales or measurement scales. And we're going to go through that now because the nature of the scale on which the observations you make exist, or the data that are generated from those observations exist, has implications for the kinds of analyses and the kinds of inferences that you can draw from them. This will be important for when next week we start to cover things like statistical analysis, and of course, when we move on to looking at qualitative data analysis as well. So here's a visual depiction of Stevens' scale theory. So we have essentially four scales on which data can lie. We have what is known as the nominal scale, the ordinal scale, the interval scale, and the ratio scale. So let's go through those now and come up with some examples that will hopefully help you understand what these scales mean. Now, the nominal scale, which is depicted within this outside box here, is essentially a scale which means that any kinds of transformations we make to the data on a one-to-one basis will ensure that they refer to the same concepts. So you can think of this in the sense of how we were discussing qualitative data the other day. Qualitative data is that which deals with discrete quantities. So for example, if we were to ask people whether or not they like strawberry ice cream, yes or no, and then we were to label those individuals, those observations that we make as yes or no, they refer to two distinct concepts. Either people do or do not like strawberry ice cream in this case. But we could make transformations to those yes and no answers. We could, for example, call all of the yes answers 1 instead, and all of the no answers 0 instead. Even if we made those transformations, if we applied that function, which was to turn yes into 1 and no into 0, we would still maintain equality of what we were referring to, as long as we didn't start to apply these values to different kinds of qualities. So within the nominal scale, we're referring to discrete objects or entities or groups of objects or entities. So for example, this could be when in your data you code whether individuals are male or female. Or, for example, you give each individual themselves that you've taken repeated measurements on an individual identifying value or code that you apply to them. So, the nominal scale refers to essentially qualities, and that's why any transformations of them need to make sure that they maintain these equalities between the concepts that those observations refer to. Now, the ordinal scale, which subsumes all the properties of the nominal scale, and I should note now, all of the higher level scales subsume all of the properties of the lower level scales themselves as well, which is why oftentimes you may hear nominal scale data as being referred to as the lowest kind of scale, and ratio scale data as being referred to as the highest kind of scale. Ordinal scale data essentially maintains this equality, but also states the relationship of greater or less than. So, a good example of an ordinal scale is something like a Likert question, or some kind of self-report. So let's say, for example, instead we were still interested in whether people like strawberry ice cream or not, but this time we wanted to ask people how much they like strawberry ice cream. Now, we could ask them this question and we could provide them with a 5-point scale with a 6-point scale from 0 to 5, where 0 is I don't like it at all, 5 is I like it immensely, and all of the other numbers exist somewhere along that spectrum. Now let's say, for example, we asked 4 people to answer our question. If I answered 1 and someone else answered 2, and someone else answered 3 and someone else answered 4. If we were to take myself and the first person who answered 1 and 2 respectively, we would see that on that ordered scale, the person who answered 2 was higher than myself. Also, the person who answered 4 was higher than the person who answered 3, and person who answered 2, and person who answered 1, and so on. But if we took, for example, the difference between myself and the person who answered 2, which was 1 point on the scale, and the person who answered 3 and the person who answered 4, which was also 1 point on the scale, we couldn't necessarily be sure that just because numerically on our ordered scale these results seem to imply that we were similarly different in terms of our degree of likeness for ice cream, all we can say is that we know that the ordering is maintained. So for example, if we were to take our scale and instead of using it as 0 to 5, we had 0, 10, 20, 30, 40, 50, we would still maintain the ordering of the responses that we got, but we would have very, very different degrees of difference between any points on the scale. So an ordinal scale maintains the order of the concept that we're interested in, but it doesn't necessarily tell us specifically what the degree of difference is or the magnitude of differences between any given points on that scale. Now, this is where interval scales and ratio scales become very, very important in quantitative research, particularly because they do exhibit properties such as known degrees of equality of intervals or equality of ratios between them. So, with the interval scale, for example, the interval scale can undergo any kinds of functions or transformations that, as long as they maintain the equality of intervals between the 2 points. So, for example, let's say we had the concept of temperature that we were interested in, and we decided we were going to measure temperature at 4 different times on the Celsius scale, and we had 4 different values. Let's say on one day, in the morning and evening, we had values of A and B, and let's say on another day we had values of C and D on the Celsius scale. Well, in this case, the difference between A and B and the difference between C and D are exactly the same. They refer to an equality of intervals. And this would be the case even if we transferred this into the Fahrenheit scale. So if we transformed it into the Fahrenheit scale, the differences in temperature would still be the same between one another. So an interval scale maintains the equality of intervals between one another. However, it doesn't maintain the equality of ratios, which is a property that ratio scale data has. And the reason for this is that interval scale data, such as temperature on the Celsius or Fahrenheit scale, does not have what is known as an absolute zero value. You can have minus values of degrees Fahrenheit or degrees Celsius. However, if instead we were to measure temperature on the Kelvin scale, which has an absolute zero value, we would be able to calculate ratios amongst the data and understand whether there is equality of ratios between them. So for example, let's take length here as an example instead, because it's an easy one to use and it's a common example used in scaling theory. Obviously, we can't have less than 0 length. There is an absolute zero value for the property, the quality, the quantity length. Anything less than it just means that it doesn't exist. So in this case, for example, the ratio of A to B is 1/3, or B is 3 times the length of A. So the ratio between them is 1 to 3. In the case of C and D, even though they are different measurements or different lengths, the ratio is the same in this case. So we can identify whether or not there are equalities of ratios between sets of values that are measured on a ratio scale, that is to say a scale that has an absolute zero value. And this is important because in many cases we need ratio data in order to be able to calculate certain things. If we're interested in ratios, then this becomes very important. So for example, an area of research that I've mentioned that I work on is the topic of effort. And in the work that I do on effort, we conceptualize effort as being the ratio of task demands to the capacity for someone to perform a given task. And in order to calculate that ratio, we need to be able to observe and measure the demands of a task or the capacity that someone has to perform a task on a ratio scale in order to be able to calculate what the effort required for a given task is. So it's very important, for example, in that area of research for us to understand precisely what kinds of scales we're working on with the observations that we make. So here's just another quick look at the scales of data. So we have the nominal scale data, which is to say kind of categories, distinct qualities, discrete objects or groups of objects that we use. The ordinal scale, which is to say observations that are ordered. We know that they are greater than or less than, but we don't necessarily know how much exactly. Then we have an interval scale, which does tell us the distance between observations, but because it doesn't have an absolute zero value, it doesn't allow us to calculate ratios, which is something we can do with ratio scale data, which maintains all of the properties of the below data, but also maintains the equality of ratios. So it's very important to understand what scales you're dealing with, because this influences the kinds of statistics, for example, you can do with data, particularly if you're dealing with quantitative data. So an example to give you here is oftentimes people will, for example, use a rating scale like a Likert scale, say it's a 0 to 5 or 0 to 7 or 0 to 10, and they will calculate things like means and standard deviations using using ordinal scale data, which strictly speaking are not admissible statistics to calculate on an ordinal scale. They need to have, at the very least, interval scale data to be appropriate statistics to use. And we have different kinds of statistics and distributions that we use for things such as ordinal scales or even nominal scales. So it's important to understand the level of measurement that you're using so that you can then consider what the most appropriate kinds of statistical analysis are to do on that data.